In this lesson, we're going to talk about silicon chips. We're going to talk about what they are, the technology, how they're made, how it's changed over the years, how it might change in the future, and what it means for everything from technological advance to geopolitics and warfare. Now, why are we spending a whole lesson talking about one particular technology, silicon chips? Why don't we talk about something else? Well, there's lots of reasons why silicon chips could be seen as the most important technology in the world today. One thing is the incredible progress. Silicon chips now are billions of times better than silicon chips back when I was born. Almost nothing else can match that incredible progress over the time. Are billions of times better? Cars today are better than they were when I was born, but they're not billions of times better. And almost all the changes in the world I've seen over my lifetime ultimately boil down to silicon chips. Your smartphones, computers, the internet, satellite communications, whatever, they all require silicon chips. Silicon chips are what allow smartphones and AI to exist. So this wouldn't exist without the silicon chips inside it. People have tried to estimate what fraction of the world economy relies on silicon chips, and most estimates are that in developed countries at least 40% of the entire economy depends on it. So it would all be 40% poorer if it wasn't for silicon chips. So the taxes generated by silicon chip based industries are actually supporting all sorts of other things like doctors and nurses and so on. Silicon chips are crucial for defense. Ever since the development of smart bombs like in the first Gulf War, it's become clear that a country that cannot master silicon chips cannot win a modern war. And chips are in everything. A typical car, even a non-electric car, will have hundreds of silicon chips in them. During COVID, when there was a disruption to the supply of silicon chips, a lot of car manufacturers had to shut down because they couldn't build the cars because they couldn't get the chips. Even electric toothbrushes, credit cards, almost everything has silicon chips in today. Now let's look at some stats about the incredible progress in silicon chips. The famous thing here is so-called Moore's Law, named by Gordon Moore, who at the time was the chair of a company Intel. And what he worked out in the 1960s was that the number of microprocessors, transistors basically, on a single piece of silicon, a wafer, was doubling every 18 months. And he wildly extrapolated this might keep going out to 1975, give you many, many orders of magnitude improvement. Did it? Well, here's the data. The number of transistors on microchips has doubled, not every 18 months, it's slowed down to once every 2 years, but nonetheless that's exponential growth. Every 2 years you've got twice as many transistors, and then another 2, 4, then 8, then 16, then 32. And this has continued from 1970 through to at least 2020. You can see this is a log linear graph, and it's showing a pretty much straight line the entire way, which means exponential growth. So you can see a cutting edge transistor back in 1970 might have a couple of thousand transistors. Now the cutting edge ones are in the tens of billions of transistors. Just a staggering amount of progress. It's very hard to think of anything else that would improve so much. I mean, just imagine that a car had improved from 1970s by 50 million times. Would it mean it could go 50 million times further without refueling, in which case no car would ever refuel? Would it be 50 million times cheaper, in which case you'd buy thousands of cars for $1? Would it be 50 million times more reliable, 50 million times faster, going faster than the speed of light? Cars have improved since then, but only by factors of 2 or 3, not by factors of 50 million. This progress has allowed other things to take place. So, for example, sometime around 1980, the chips, which by that point had a few tens of thousands of transistors, were now becoming powerful enough that you could actually have a computer on your own desk, a personal computer. You didn't need to have a big mainframe in the office down the corridor. By the year 2005, when we're talking about 500 million transistors on a chip, smartphones become possible. Before that, the energy demand would be too great, but because every processor is so much smaller on the chips by this era, you could feasibly have a computer that could run off battery power. It wasn't possible before that. And most recently, sort of 2015 and 2020, where the point at which we're at the many billions of transistors on every chip, That's allowed large language models for AI to exist. Again, current technology for AI could not have existed at any previous time. It relied on this incredible speed of the chips. Now this graph here is showing transistor count. What probably matters more to you is the number of calculations per second per dollar, and here's a graph showing that. It goes all the way back to mechanical calculators in the first part of the 20th century, then relays and vacuum tubes, transistors, and then integrated circuits. And you can see once again it's a log linear graph, exponential growth over the entire 20th century and 21st century so far. Staggering progress. And it's not just the ability to do calculations that's improved. The memory and storage. Here's a graph showing the cost in dollars per terabyte of storage, how that's dropped from the 1950s through to the present. And again, we're talking many orders of magnitude of drop in the price. So how much storage you can get per dollar. So that sounds absolutely spectacular. What's causing this incredible progress? And we'll talk about that. But you have to bear in mind that this progress is actually becoming harder and harder. It turns out there are about 20 times more scientists in the world working on improving semiconductors today than there were back in the 1970s. But the rate of advance is about the same. It's still doubling every 2 years. So back in 1970 it took maybe 1,000 researchers over 2 years of work to double the speed of computers, whereas now it takes about 20,000 researchers over 2 years to double the speeds. So are the scientists really 20 times less productive now than they were back then? Possibly. Or is it getting just really hard? And this factors in to the cost. This is the cost of a fab. Now, a fab is a fabrication plant. It's basically a factory that makes semiconductors. And back in the 60s and 70s, a fab would cost a few tens of millions of dollars. Not pocket change, but $30 million. That's something that most countries could have and most companies could raise some money to produce, and that would produce the cutting-edge chips of the time. But that was a long time ago. The price went up to hundreds of millions of dollars by the 1980s, by about $1 billion, and currently we're talking maybe 20 billion US dollars to build a modern fabrication plant, a modern fab. So yes, the chips are getting better, but the research to produce a better chip is becoming way more expensive. Far more researchers are involved, and the cost of building these things is staggeringly high. So what this means is that while you can pack ever more transistors on a chip, it's no longer clear that it actually makes the computing faster. This is the cost of 100 million transistors compared to what it was for in the 28 nanometer process, which would be about 10 years ago. And you can see that before that, the cost per transistor was going down. Since then, we're still packing ever more transistors on a chip. The chips are getting more powerful individually, but they're also costing more. And so the actual cost per 100 million transistors has arguably stayed fairly constant. So maybe we still like the new chips because they're more power efficient and they can communicate better if everything's on the same chip. So you absolutely need these things for the cutting edge smartphones and for the chips used to train artificial intelligences. But it's no longer getting cheaper to get compute.